going to be Allesandro. So feel free to take it away.
Hello, everyone. It's me again because Allesandro.
Sorry.
Yeah, he actually can't make it, so I'm going to give his presentation. We are going to be talking about the rifting process on Venus and basically what the kinds of numerical models we did to gain some insights. I'm going to be saying next a lot in this because Allesandro likes to make slides with lots of builds. So next slide, please. Yeah, so there are observations of rifts or fault like structures on Venus, and it's kind of unknown how they could occur there under this high temperature and pressure. I'm going to go through most of what we did. If you want more details, there is a preprint that is listed here that you can look at with all the time of the world. So on the next slide, let me show you the map of Venus with some, the rifts that have been mapped on Venus. And next, we will be using a numerical code called Falcon. And next, we basically want to assess the effect of Venusian surface conditions on the rifting process, because it's a very well-studied problem in earth sciences and earth geodynamics. But we just wondered how this would translate to Venus and if it would translate at all, basically. And then next, we want to study some of the effects of rheology, because that's, of course, always a big button we can turn in these kinds of models. And then next, we also wanted to compare a bit to what limited data we have on Venus. So next, I will show you the model setup. There is a table there with all the numbers if you're interested. I think you can look up the presentation online afterwards. But basically what's important is that we have this rectangular box and we pull on both sides. We make sure that there is initialization of localization and strain in the middle by having this little weak seed. And then on the left-hand side, you can see our Earth setup, which has a thicker lithosphere and it's colder. And then on the right-hand side, we have the Venus setup, which has a thinner lithosphere and it's hotter. And that is basically what we're going to do. And we're going to tune some parameters to see how the rifting process would work on Venus. So on the next slide, we have our reference Earth model. And we're going to basically start from this and then build up to see different parameters and how they work on Venus. So here you can see all the things that on the right of the things that we will change. So if you click on the next slide, you can see that in the beginning, this is the time evolution, starts at 0 million years and goes to 10. We have symmetric conjugate faults, but then next we very quickly start to go into asymmetric rifting, and there's a lot of strain accumulation. And then next, you will see that there is mantle upwelling, and there's also some melting, which is this dark brown color in the middle there. And then next, you can see that there is some topography that is being developed. So this is basically a pretty standard rift model for the Earth. But the question, of course, is what happens on Venus? So next, we have our first Venus models. And the first thing we tested was, what is the effect of the higher surface pressure, the different gravity acceleration, and then, of course, the surface temperature on Venus. And that is what we show here. So next, you can see that panel A is the Earth model, which we just saw. And then in B, we added the pressure of Venus. C, we only have the gravity of Venus. And D, we have the pressure and gravity of Venus combined. And you can see that there's not really that much of a difference. It all shows asymmetric rifting, more or less similar. So this is not the big game changer. But next, if you actually use the surface temperature of Venus, there is no strain accumulation at all. Nothing happens. It's way too hot for any kind of brittle deformation in our models. And this is, of course, not what we know is happening because we've seen these kinds of rift structures on the surface. So our models are possibly missing something. So next, if you try and have a thicker lithosphere and see what happens. There is some kind of strain accumulation, even under the temperatures of Venus, but it's not visible at the surface. It happens below the crust. So we need some other ingredients to actually make some rifting happening on Venus. So in the next slide, the first thing we tried was make the crust stronger. So instead of the typical quartzite crust that we use in these Earth models, typically, we now try a dry diabase crust with the temperature conditions of Venus, and we use different methods of initializing the deformation, either in the middle, or a seed, in the mantle, in the crust, or a bit more distributed. So if you click on the next slide, we see that now actually some things are happening, and there is faster evolution for the crustal and the random seed. And then next, there is actually some strain that is being accumulated, but there is still no mantle upwelling and melting, what we would expect to see in a rift on Earth. And then next, we see that there is some topography, and there's also some heat flux associated with it. But it still doesn't really look like the surface features of a rift that we see on Venus and any rift on Earth, basically. So in the next slide, we thought, okay, we've used a 35-kilometer crust so far. What if we thin the crust a bit? Would we get more localization and actual rifting on Venus? And if you click on the next slide, you can see that, yes, there's actually faster evolution again, and there is some kind of mantle upwelling now, as well as melting that we can see. And then on the next slide, we have these wider and deeper basins, and there is some topography that's being created. So this is definitely going in the right direction. So next slide. We thought, well, we've made the crust stronger, diabase crust, but there's also obviously very little constraints on the rheology of the mantle on Venus. So maybe we can also try some models with a stronger mantle. So instead of what we had before, we now have a dry dunite mantle, so it's a bit stronger. And again, we want to see if we can get these rift-like features. So next, there you can see that there is some strain accumulation, but it is quite broad again. And there is again no mantle upwelling or melting. And then next, you can see that there is similar topography from what we've seen before, and similar heat fluxes, but no rifting as we would expect it on Earth, perhaps, or the narrow bands that we see on Venus. So in the next slide, we thought, okay, what if we then combine the strong crust with the strong mantle and the thin crust? Because again, just now we had 35 kilometers and now we have 25. And then we see the following. As if you click on next, it all goes a lot faster, and we see this rift-like structure, this upwelling of the mantle, and as well as melting. And then in the next slide, you can see that there's actual topography being created, like wide and deep basins. This aligns with, what we think of as rift topographies. And we see high heat fluxes corresponding with the opening of basins because you have this mantle upwelling. On the next slide, we can then discuss what is happening. Because we ran a lot of models, I showed you a lot, and it must be pretty overwhelming. But this is a summary, and the way it works is as follows. We are looking at three things that we think characterize rifting. The first one is strain localization. The second is mantle upwelling. So do we see the mantle going up? And then the third one is there any melting involved? Then on the x-axis, we have the different types of initialization of strain in the middle of the model. So if you have a seed in a mantle or a seed in a crust, etc. And then on the y-axis, we have the different rheologies that we tested, with at the bottom, the weaker rheologies, and at the top, the higher rheologies. And we also have the different crustal thicknesses. So what this means is that for each of the 3 things we're interested in, we're showing the same models and we're evaluating how each model is doing in each of these 3 things. It can be red and an unhappy face if it doesn't have any strain localization, for example, or it can be a happy face if it does show what we want for rifting. So in the next slide, you can see that at the bottom for the weak crust and weak mantle, there is no strain localization, there's no mantle upwelling, no melting, there's no rifting basically. Venus is too hot, it doesn't work in our models. In the next slide, you can see that if you have a stronger crust, you will have strain localization that looks like rifting, and you will have mantle upwelling. You will have something that resembles a rift, which is exactly what we wanted and what we were looking for. So this is very promising. And then in the next slide, you can see that if you have a thin crust in these models, you will have melting. So let's go to the next slide and briefly compare to Venus. So this is just a plot of the heat flux in our models, which kind of aligns with the global average. And of course, in rifts, because there's active upwelling going on, you expect a higher heat flux, with thinner crusts having higher heat fluxes. And in the next slide, we compare it to 2 profiles of rifts on Venus, namely Ganus Chasma in red dashed line and Dvana Chasma in the black dashed line. And you can see that the blue models are kind of more in line with the red dashed line, which is Ganus Chasma, whereas the yellow models are more in line with the black dashed line. And these different models are different thicknesses of the crust. So maybe this is an indication that these kinds of rifts have different thicknesses of the crust, with Ganus Chasma having a little bit of a larger thickness of the crust and Dvana Chasma having a little bit of a thinner crust. So then we come to our conclusions in the next slide. We see that there is almost no significant effect of gravity and pressure on the evolution of rifting, but the high surface temperatures of Venus really make a big difference in localizing strain and getting these rift-like features. So next, if you want to have some kind of rift features developing, you need a very strong crustal diabase rheology. And next, the thin crust enables some melt to form. So, if you want to say Venus is currently volcanically active, you need to have some melt that is being developed. A thin crust facilitates that. And then next, the surface topography fits well with the 2 profiles we looked at. And then on the last slide, these are just all the people that worked on this project. And thank you very much for listening.